Chapter 6.5, we're looking at the complex plane. We're going to plot complex numbers in the complex plane and find absolute values of complex numbers. We're going to perform operations with complex numbers in the complex plane, as well as use the distance and midpoint formulas. So the complex plane. So just as a real number can be represented on the real number line, a complex number the complex number z equals a plus bi can be represented by a point AB in a coordinate plane, and it's called the complex plane. So here is an example of the complex plane. So notice that we have our real axis is the x, the imaginary axis is our y. And so what we're going to do in the beginning is find the absolute value. So the absolute value, are called the modulus of the complex number z equals a plus bi. It's the distance between the origin and the point AB. So we're just trying, when we're finding the absolute value, we're finding the distance from that point to the origin. And then just as an FYI, the plural of modulus is moduli. So the absolute value of the complex number z equals a plus bi is the absolute value of a plus bi equals a squared plus b squared. When the complex number z equals a plus bi is a real number, so if b is 0, right, if this becomes 0, this definition agrees with the given for the absolute value of a real number. Because if we plug it in, a plus bi equals square root of a squared plus b squared, which is absolute value of a, right? So whenever we're trying to find like the absolute value of -3, we know that is 3, right? So that holds true here. So example 1, we're finding the absolute value of a complex number. Basically, we're finding out how far is it from the origin. So plot z equals -2 plus 5i in the complex plane and find its absolute value. So that should be really fast. So remember that the x-axis is the real part, and then the y-axis is the imaginary. So how you plot this is -2, that is left 2 and up 5. So -2, 5, and so we're trying to find this distance here. So to find that, it's the absolute value of z equals the square root of -2 squared plus 5 squared. So that is 4 plus 25, or the square root of 29. So that is the distance. So try this example. Plot z equals 3, -4i in the complex plane, and then find its absolute value. Right, if you tried this out, you should have gotten this graph, and then you should have found that that distance is 5. So the complex number z equals a plus bi, just as a note, z equals a plus bi, can be represented by the vector, so u equals ab, right, in component form. So for example, if you have z equals 1 plus 2i, then we can write it as a vector, u equals 1, 2. And then to add complex numbers geometrically, first you represent them as vectors, then you add the vectors together. Okay, so just so you understand what we're doing next. So let's add in the complex plane. Find 1 plus 3i plus 2i in the complex plane. So what it's saying is that we can represent these as vectors. So let's say this is u and this is v. So we can write it as u, and that equals 1, 3. And then v, and that equals 2, 1. Then we can add the vectors together like we did previously. So this is going to be 1, so these together, the horizontal component together, 1 plus 2, and then the 3 plus 1. And so therefore, this is going to be 3, 4. And then we can rewrite it as 3 plus 4i. Okay, so really this is just talking about really focusing on vectors and how to do it using vectors. So we can graph it. So if we have u, which is right 1, so just remembering from the beginning chapters, so this is right 1, up 3, here is our first vector u, and then our second vector is right 2, up 1, so right 2 and up 1 would be here. And then, so that's v. Then we're looking at a resultant vector here, and that would be at 3, 5. 4. You don't have to draw it for this next one, but I do want you to find 3 plus I plus 1 plus 2I in the complex plane. So it is trying to test you on whether you can add vectors or not, so try to do it with the vector, using vectors, please. All right, so you should have gotten 4I plus 3. And I know you could really do this all in your head as well. So now let's subtract in the complex plane. So find 4 plus 2I minus 3 minus I in the complex plane. So again, it wants us to do it with the vectors, and so we can write it as U equals 4, 2, and then V equals 3 and negative 1. Now remember, when we are subtracting vectors, what we want to do is we want to distribute the negative. So this is going to be negative 3 and a positive 1. So if we needed to draw it, then you subtract the horizontal component or you add the horizontal component and the vertical component. So therefore this is 1, 3 or 1 plus 3I. So try this one. Find 2 minus 4I minus 1 plus I in the complex plane. Okay, if you try this out, you should get 1 minus 5I.